Thank you, and hello everyone. Today we are presenting real-time multilingual custom keyboard spotting. So you may have heard of wakeboards before. They are the phrases that activates voice assistants such as Alexa or OK Google, and wakeboards have become an integral part of our daily lives, part of a voice assistant in smartphones, smart devices, and EV cars. But for a business owner that wants to distinguish its brand from others and wants to establish a strong connection with its customers, generic keyword nature may not be in line with its brand image. So custom keyword spotting provides an excellent opportunity for businesses to deepen their user engagement with their brand by creating a lasting impression through personalized or keyword spotting. And even if the business don't currently utilize voice assistant, this solution has a potential to be valuable in other applications, such as keyword spotting in mental health monitoring, like depression detection, or other applications such as detecting keywords or phrases in phone calls or audio recordings. So that's why the solution that we are proposing in this work, it has the following features: real-time audio processing, low processing time, about 35 milliseconds per 1 second audio chunk. It has a high performance based on the false acceptance and rejection rates. It works on 50 different languages, and it's robust in presence of various background noises. And the ML model pipeline that we are proposing in this solution has the following steps. First, we are asking a user to select their keyword and record their voice while repeating their desired keyword. Once the recording is completed, then we pass the audio clip for pre-processing, removing the noise, and segmenting the audio clip to 1 second speech files. And then we pass these audio files to the data preparation, augmentation, and fine-tuning the keyword spotting. Once the training and fine-tuning is completed, then the user can test the model in real time and see the prediction result, whether it's background noise, other words, or their desired keyword. For customizing the keyword spotting, we use the few-shot learning. And here we are, after we segment the user's speech file, we only use the 5 speech file for the training and the rest for validation. But 5-shot is not enough to fine-tune the model. That's why we utilize the various data augmentation approach to increase the 5 to 1,000 data samples. And the approaches that we use in data augmentation are adding background noise, time shifting from negative 100 millisecond to positive 100 millisecond, and also another approach called spec augment, which is time and frequency masking. So once the data augmentation is completed, then we can fine-tune the keyword spotting model and predict whether the audio is background noise, non-target word, or keyword.
As we can see by the solution architecture diagram, our front end captures the user's keyword and spoken voice recording in real time or in the upload. It's sent to a fast API endpoint, which is both hosted on AWS EC2. It's then segmented using a Hugging Face model into 1 second audio clips, and then fine-tuned with few-shot learning to produce a personalized model that's ready for inference. And we'll see that in the demo next. The demo.
Hello. Today, we're going to be demoing the multilingual custom few-shot keyword spotting app that we created. And first, we're going to enter our keyword that we're selecting. So, hey, FourthBrain, or hey, MLE in this case. And we're going to type it in and press enter. And then we're going to upload a WAV file. And the WAV file is going to include us just repeating that keyword, hey MLE, 10 times at least. And what you'd want to do is say it kind of faster, slower, high pitch, low pitch, and then submit that WAV file for training. So we're going to click training, and after a few minutes, fast forward, now our training is complete. and we have a fine-tuned model that's customized to our wake word. So what we can do is we can upload another file, or in this demo, just the same file, and we can see that we got a prediction back, and we're going to see what that prediction says, whether it detects the keyword, whether it detects another word, maybe it's not MLE, maybe it's guaca, and maybe it's just some awkward silence for that joke.
So in the result, as we can see, one of three classifications. There's the keyword, there's possible other words, or some background noise, which occurs above a 90% confidence threshold. And now on to the next part of our demo.
So in the next demo, we are showcasing the real-time processing feature of our solution that is running locally via a Streamlit app. See here, the second demo is very similar to the previous one. The only difference is that instead of asking a user to upload the audio file, here after they select the custom keyword, they need to record their voice while repeating the keyword. For this demo, I chose the custom keyword as "Hey Sushi," and I'm going to repeat the "Hey Sushi" for 20 seconds. Hey Sushi. Hey Sushi. Recording is complete. So once the recording is completed, then similar to previous demo, we can go to the next step and fine-tune the model by pressing train button. Once the training is completed, then the user can test the model in real time. Once fine-tuning is completed, now we can test the custom keyword spotting model in real time by pressing Start Inference. And the loading the fine-tuned model may take a few seconds. Once it's loaded, it will capture the audio and predict audio chunks. As you can see, initially when I didn't speak, it detected the audio as a background noise. Now I am talking and it detects it as other words. Let's try to say the keyword. Hey, sushi. As you can see, the model is able to distinguish the custom keyword from the other voice and background noise. So in summary, the solution that we are delivering is an end-to-end real-time multilingual custom keyword spotting, and we evaluate the performance of this model via qualitative and quantitative metrics, and we deploy the model on AWS EC2 through Streamlit as front-end and Fast API as back-end.
And while our delivered solution is impressive, we wanted to be sure to consider responsible AI throughout this entire process, primarily by protecting user data through ensuring secure handling of the recordings, considering both fairness and being unbiased in our selection, as well as our data set and in our training. And in future work, we hope to prevent improper uses. Speaking of future work, in the next slide, we can see that we hope to improve our real-time audio processing with multi-threading and multi-processing, improve our performance of the model by incorporating echo, double talk, and speech diarization, which are audio processing techniques, continue to improve our responsible AI approach, as well as the handling of simultaneous usage on various cloud platforms with multiple users, and then embedding our model into edge devices such as smartphones. And finally, we'd like to thank all of our instructors, FourthBrain, as well as our classmates in the MLE 11 cohort, and all of you for participating in today's demo day.